Hey everyone, how's it going? So today I'll be looking at this particular Kaggle competition again in the NLP space, that is student writing feedback. And just few days back, I did one model of long former on this competition with TensorFlow, and today it will be Roberta-Large with PyTorch. Now, one specialty of this particular Kaggle competition is that many have applied long former model to deal with these challenges here. And there is a reason behind the focus on long former in this competition. Let's quickly go over that. So for regular transformer architecture, that has a matrix multiplication that scales quadratically with the input sequence length in terms of memory, making the regular transformer very expensive for longer sequences. And that's exactly the reason that we have 512 token max length in a BERT-like structure. And as a partial solution to this, we have long former and big BERT. So in the long former models, the attention mechanism is designed to enable efficient processing of long sequences. It differs from standard self-attention mechanism in few key ways. One is the sliding window of attention. So instead of attending to all positions in the input sequence as in standard self-attention, the long former attends only to a sliding window of adjacent position. This reduces the computational complexity of the attention mechanism from order of n square to order of n, where n is the length of the input sequence. And with long former, the lower cost of sparse self-attention mechanism allows these models to handle up to 4096 in regular GPU, that is 4096 of input token length, which is almost 8 times what a normal transformer like BERT can handle. Hence, given the length of the text in this competition, many have focused on long former type models. However, the classic 512 token models such as BERT do have a mechanism to handle sequence length greater than 512 tokens. And what are those mechanisms? So there are a couple of ways. First, split it into chunks of 512 tokens with some overlap with the stride parameter. Then use the model to process those chunks. And finally, march back the predictions over the chunks to obtain predictions over the full length of the text. And we will kind of pursue this strategy in this exercise today. Now, let's quickly look at the classification problem in this particular competition. So basically, we have a bunch of essays written by kids in the age of around 12 to 18 years old. And in which we have to find word sequences that can be classified as one of the 7 discourse types given in this essay. And what are those discourse types? They are these one: lead, position, claim, counterclaim, rebuttal, evidence, and concluding statement. So lead means, for example, they have given the definition here that it's an introduction that begins with a statistic, a quotation, a description, or some other device to grab the reader's attention and point toward the thesis. Interestingly, this is not present in all the training set data. Around 40% of the IDs do not have a lead. Similarly, position is an opinion or conclusion on the main question. Around almost all the training data has position. However, it is not always at the beginning. And so if you click on these train.csv right in the Kaggle official page, you can see all these discourse type here under this column heading discourse type. So we can see lead, position, evidence, all these things. So they are associated with a particular ID. And this ID actually refers to a text file, and the text files are all in this train folder. So I think we have around 15,000 .txt file, and each file is identified with a particular ID, and that ID is what this first column represent. And yeah, so let's go ahead. So here in this competition, basically we are tasked with giving feedback on argumentative essays written by students. Specifically, our task is to predict the human annotations. This annotation will be done in 2 steps. First, segment each essay into discrete rhetorical and argumentative elements, and then classify each element as one of the 7 discourse types that we just seen. And now quickly go over the basics of the training data here. So we have a bunch of text files and a separate trend.csv that we just saw. In the CSV, we get a reference to the text files and then multiple lines per text file with spans indicating a specific discourse type. So if you just look at this trend.csv, you will see each single ID is occurring multiple times. And that's because they represent different spans of the same writing. That is, within each .text file, we have different spans, and those spans needed to be classified according to one of the discourse types. And that's the reason we see multiple IDs occurring in the trend.csv. And going over these column heading, so ID is the obvious one, ID code for essay response that represent each single .text file. And then discourse ID. So discourse ID is a unique identifier for each discourse element. Basically, each row in the trend.csv contains one discourse element, and the discourse ID is what identifies each of these discourse elements. It is different from the ID column in that the ID is the identifier of the full student essay that the discourse element came from. So multiple rows can have the same value for ID, just as what we are discussing, because each of the rows represent actually one unique discourse. So on the other hand, each row in the trend.csv will have a different value for the discourse ID because they represent each unique discourse. And then we have a discourse start, which is a character position where discourse element begins in the essay response. Similarly, discourse end is a character position where discourse element ends in the essay response. Discourse text is obviously the text of the discourse element. Discourse type is a type. Discourse type number is an enumerated class level of discourse element. And finally, we have this prediction string, which is this is the word indices for the training sample as required for predictions. Now, one very important part of this competition is the evaluation metric. We need to really understand how this is calculated here because it's slightly not so trivial. So what it says here for the evaluation metric is that if the overlap between the ground truth and prediction is more than 0.5 and the overlap between the prediction and the ground truth is more than 0.5, the prediction is a match and considered a true positive. If multiple matches exist, the match with the highest pair of overlaps is taken. Now let's understand this. The overlap between the ground truth and prediction, this is a measure of how many words in the ground truth match the predicted words. It is calculated as the number of words that appear in both the ground truth and prediction divided by the total number of words in the ground truth. So for example, if the ground truth for a sample contains 10 words and the model predicts 8 of those words correctly, the overlap between the ground truth and prediction would be 0.8 or 80%. On the other hand, the overlap between the prediction and the ground truth is a measure of how many words in the prediction match the words in the ground truth. It is calculated as the number of words that appear in both the ground truth and the prediction divided by the total number of words in the prediction. For example, if the model predicts 12 words for a sample and 10 of those words match the words in the ground truth, the overlap between the prediction and ground truth would be 0.83 or 83%. So take this example, so it will be much more clearer. So here in this example, ground truth are 1, 2, 3, 4, 5 and prediction is 1, 2, 3. So common indices between the ground truth and prediction are only this 1, 2, 3, that is 3 common indices. So overlap between the ground truth and prediction will be 3 common indices divided by the number 5 because I have 5 ground truth. So the first ratio will be 0.6, which is more than 0.5 as required by our criteria. Now we have to calculate the second overlap, which is overlap between the prediction and the ground truth. So again, we have 3 common indices divided by number 3 here, because the total number of predictions are only 3. So this gives a ratio of 1, which is again more than 0.5. So since both the overlaps are greater than or equal to 0.5 as required by our evaluation metric criteria, this particular prediction is considered a match or a true positive. So the important point here is that in both, the numerator is the size of the intersection. Both calculations have to be at least 0.5 for the prediction to be considered a hit. These two measures are used together to determine whether a prediction is a true positive or not. By using both measures, the evaluation metric ensures that the predicted words are not only present in the ground truth, but also that the ground truth words are correctly identified by the model. In some cases, there might be multiple matches. If this happens, that is, if multiple matches happen, the competition rules state that the match with the highest pair of overlaps is considered. And the competition rule also says that any unmatched ground truths are false negatives and any unmatched predictions are false positive. These statements means that any ground truth without a corresponding matching prediction is considered a false negative, that is, missed correct prediction, and any prediction without a corresponding matching ground truth is considered a false positive, that is, incorrect prediction. So I'm in my VS Code, and of course you will have the full access to the code in the description of the video, the GitHub link, please check it out. And as to the file structure of this project, I have 4 files, actually 5 files. I have these main notebook, then the individual Python files for validation, for all the utils method, for the training method, and the constant method. So in the const.py file, I have all the basic constants defined here. First is your root directory. So if you are directly using it in Kaggle, your root directory will be this. I was also running this notebook in locally. So I have my root directory defined, and model name, this is where you define your Hugging Face model that you are using. So here I was experimenting with both Roberta-Large and Roberta-Base. So Roberta-Large is definitely the preferred one. All right, and then max length 512 doc stride. We will come to this stride concept little after a while. And here are all the config for the training. Note that to run it relatively faster, I have used a batch size of 1, but you can experiment with different batch size, maybe 4, 6, 8, etc. Running it for 5 epochs, and learning rate, I have 5 of them for 5 different epochs. And otherwise, nothing much. All right, this max grad norm, it will be required for our gradient clipping later during the training, and I've set it to 10. And this is my output labels. This just reflects the actual class names or the label names for the different NER as given in the Kaggle's data. All right, and these are 2 constant I'm defining. They are both dictionaries for the values and keys coming from output labels. All right, let's come to the main notebook, Jupyter notebook. You have all your imports here, and also obviously you are importing all the methods defined in the other Python files. And you set your cooldown to use your GPU, and then just read the train.csv as directly from Kaggle. And this is our data. So we have ID, discourse start, discourse end, discourse text type, discourse type number, and prediction string. We already have discussed this in detail. And then I'm just going to do some very basic EDA. So I'm just creating a copy of the original data frame. And yeah, so here I am just adding few column names so that I can do a quick plotting. Basically, I just want to get a sense of the frequency and relative position per discourse type. So I have this new column name discourse type. I have this new column name discourse len and pred len. And they're basically just taking the length of the discourse text column and prediction string column within lambda function. And columns to display, I'm defining only, I'm taking few columns, and then I am using a plot here to get the average number of words versus discourse type, and also the frequency of discourse type in all essays. And looking at the graph, there is a correlation between the length of discourse and the class. And evidence is the longest discourse type. We can see here this top one. And when looking at the frequency occurrence, we see that the counterclaim and rebuttal are relatively rare. Next up, I want to create a modified data frame from the original data frame by having these two extra column names, text split and entities. And you can see these entities is where I have the NER, that is named entities, attached to the corresponding word. And what are these text? Actually, these texts are coming from each of the .txt file that we have within the train folder. And then these entities, for example, phone, this is attached to these O entity. Similarly, I have B lead, I lead, and all these things. And that's for that I have to define a util function, and this is that util function, attach NER to text. And that's defined within the utils method here. That's my function. So this particular method convert text words into NER labels and save the result in a CSV file. This function reads text files from the specified input directory, process the text, and creates a data frame with NER labels for each word in the text. The resulting data frame is then saved as a CSV file. So let's quickly go through the steps in this file, what I'm doing here in this method. So first, right in this line, I'm just looping through os.listd, that is each file within my input directory, and then remove the .txt extension from the current file, name f, and append the result to the train names list. And next, open the current file, read its content, and append the text to the train text list. And then you define a new data frame, df_ner text. It will have an ID column and text column. Next line, add a new column, text split, to the df_ner text data frame, which contains a list of words in the text column. And after that, initialize an empty list all entities right here, which will store the NER labels for each word in the text. And then I start over this loop, and this loop is using iter rows. This row right here in the loop will give you that particular row or your current row. So in the next line, I'm getting the number of words in the current row's text split column and storing it in the variable total with this len row text split. And then create a list entities with the same length as total, initializing all elements to the label O. That is, here O stands for outside in the context of NER, that is named entity recognition, meaning no entity. And that's how I'm initializing the entity's elements. And then I start my second loop over here, and this time I'm looping over this df train org data frame. And here get the discourse type value from the current row in df train org and store it in the variable discourse. Next line here, that is list ix. Here I'm converting the prediction string value in the current row of df train org into a list of integers and store it in the variable list underscore ix. And then next up, entities here, assign the label B discourse, for example, maybe B lead or B position, etc. to the first element of the list ix in the entities list. So with list ix0, I am grabbing the very first element, and that's I'm assigning with the B tag. B stands for beginning here. And then for the rest of the elements here, that is this loop right here, That's for taking care of the intermediate labels. That is, I'm assigning the intermediate I label to all the words in the entity except the first word, which gets a beginning B label to indicate that they are part of the same entity. And this is a loop that iterates over the element of list ix starting from the second element, that is index 1, until the end of the list. And list ix contains the indices of the words that are part of the entity, that is discourse, in the text. The first element, that is index 0 in list ix, is assigned a beginning label. So we start iterating from the second element here, that is index of 1, to assign intermediate label to the remaining words. So in this way, your all entities variables gets completely updated with the individual entities, and you have your all the constructor of your data frame ready. And hence I am making this entire df-ner text into a CSV with 2 CSV, and that's what I'm also returning from this entire function, which is my function that's attach ner text. And when I apply this attach ner text in my notebook right here, that's how I get these df-ner text with all the relevant headings that I wanted. That is, here in the last column, I have the ner attached to each of the text for each of my .txt file. And the next line, this assertion statement here, is for checking that we have created one entity label for each word correctly, because I need to check that we have not missed that, or there is no mismatch. So here this str.len computes a length for each list in the text split column. The .str accessor is used to perform a vectorized string operation, and the .len method computes the length of each list. And at the very end, these all that method checks if all elements in the resulting Boolean series are actually true. And after the assertion, I'm ready to do the train and validation split. So here I use a 90% and 10% division between my training set and valid set. So first I'm making use of np.random.seed so that the results are reproducible, because next I'm using np.random.choice. So for the train index, first I am selecting a list of indices with this np.a range. This function generates an array of evenly spaced values. In this case, it creates an array of integers starting from 0 up to the length of IDs all unique. And this array represents the indices of the unique IDs. And then after selecting those IDs, I'm applying np.random.choice, which will generate a random sample from a given one-dimensional array or range of integers. It can be used to select random elements from an array or to create random samples without replacement. The second parameter of this np.random.choice is the output size, which I'm defining it to be 90% of the length of the entire unique IDs. And replace equal to false means each element can only be selected once. And once again, remember that I have set np.randomSeed equal to 42, which will set the random seed for NumPy to ensure that the random sampling will produce the same results each time the code is run. This is useful for reproducibility. All right, now my train indexes are selected. So for selecting the rest of the element, I am using np.setDiff1d. That is, the rest of the elements will be my valid or validation indexes. So this np.setDiff1d function is used to find the difference between two arrays. In this case, it computes the difference between the array of all indices and the selected training indices. The result is an array containing the indices that are not present in the training set. So this not present one will be my valid indexes. All right, now that you have your indices for both train and valid, creating the data frame is easy with the LOC function. So you just apply this .loc method on your data frame and the isIn method. And in these two lines, I'm using a reset index drop equal to true. This call is used to reset the indexes of the data frame after filtering out some columns. because by default, when columns are filtered from a data frame, the index remains the same and the original index values are preserved. However, in some cases, such as when joining or merging data frames, it can be helpful to have a simple sequential index with no missing values. So by setting drop equal to true, the old index is dropped and the new sequential index is created. The copy method is used to create a copy of the data frame with the new index instead of modifying the original data frame in place. Next up, I'm just downloading the Hugging Face model, in this case Roberta-Large, to my machine. That is, it could be your cloud machine in Kaggle or your local machine. So for this, I'm just using a little util method, download HF model, which I have defined in the utils file. And this is very boilerplate code following Hugging Face documentation. So first, you define your tokenizer with autotokenizer.from pretrained, and you pass your model name. And then I am using this tokenizer.save pretrained. So that is to save the tokenizer in disk of your relevant machine. And remember, to use a save pretrain method, you need to first create a model or tokenizer object, which can be either a pretrained model provided by Hugging Face or a custom model or tokenizer that you have trained yourself. Once you have the model or tokenizer object, you can call the save pretrained method on it and provide a path where you want to save the serialized model or serialized tokenizer. Next up, initialize these config model. Here I'm initializing a configuration object for a pretrained model. The autoconfig.from pretrained, this particular method here, this method is used to automatically retrieve the configuration associated with the specified pretrained model from the Hugging Face model hub. The configuration object contains various settings and hyperparameters that define the architecture and behavior of the pretrained model. This can include the number of layers, hidden layer sizes, attention mechanism, activation functions, dropout rates, and many other options that can affect the model's performance and computational efficiency. And I am also passing num labels 15 because that's our total number of classes in this project. And finally, save pretrained again to save the pretrained model. And then the actual model, that is auto model for token classification .from pretrained, you pass the model name. In this case, I'll be passing the model name later as Roberta-Large. And your config is your config model that we have defined here. Now, and of course, you after these backbone of your pretrained model need to be saved in your disk backbone.save pretrained. That's what, and you pass the model path where I'm saving it. Now, one quick point here, that why do I need tokenizer.save pretrained here? That is, I'm talking about this line, tokenizer.save pretrained. So in most cases, you would need to save the tokenizer in addition to the model, because the tokenizer is an essential component of the model. The tokenizer is used to convert raw input text into the format expected by the model, and it is also used to convert the model's output back into text. When you train a model or fine-tune a pre-trained model, you typically also train or fine-tune a tokenizer to handle the specific input data and output format of your task. If you do not save the tokenizer along with the model, you would not be able to use the model for inference or further training without the corresponding tokenizer. And additionally, saving the tokenizer along with the model ensures that the same vocabulary and encoding scheme used during the training are used during inference as well. If you were to use a different tokenizer during inference, you could encounter encoding mismatches or other issues that could negatively impact the model's performance. In summary, you do need to save the tokenizer along with the model to ensure that you can use the model for inference or for the training, and to ensure consistency between the encoding scheme used during training and during inference. And next, I define a small util method here, get labels for word IDs. This function is for creating a mapping between the text split and entities. So basically, given word IDs, I need to get the labels of that. And remember here, word IDs is of the form something like this. It's a list of the indices. And these word IDs are actually the output of word IDs method of the encoding object, which returns a list of indices where each index corresponds to the original word in the input text for each token. It is useful when you want to have a map between the tokenized text back to their original words. So in this method, what I'm doing specifically this for loop right here. So for each word index in word IDs, it checks if the word IDX is none. If it is none, this indicates a padding token. So the function appends a -100 to the label IDs list in that case. And if word IDX is not none, it looks up the corresponding label ID in the labels to IDs dictionary and appends this value to label IDs. And finally, from the entire method, I return label IDs. Now the question is why I'm appending only -100. So the primary reason for choosing this particular number of -100. Now the question is, in this case, why this specific number of -100? So the primary reason for choosing this specific number is that it is outside the typical range of label IDs used in named entity recognition projects and other NLP tasks. By using the value of -100, which is unlikely to collide with any valid label ID, it allows the loss function to easily identify and ignore these padding tokens. This ensures that the model does not learn from these padding tokens and focuses only on the actual input tokens and their corresponding labels. And also note that you could use a different value to represent padding tokens as long as it doesn't conflict with any valid label IDs. So you could actually use -200, -300, etc. And also in this case, remember, you would need to modify the masking mechanism in the loss function to accommodate the new value. However, the choice of -100 has become a convention in the PyTorch community. So using this particular value helps maintain consistency and compatibility with existing code and pre-trained models. And then the all-important tokenize method. This util method is for tokenizing mechanism on my input training data. And so I pretty much start with this tokenizer here. That's the most important part in these entire methods. And this tokenizer is the Hugging Face tokenizer. So if I go back to the Jupyter notebook, this is where I'm defining this tokenizer, which is auto tokenizer from pre-trained. And then this is a tokenizer that I'm passing as an argument to my tokenize method. And so let's go back to my tokenize method. Yeah. So let's quickly go over these parameters that I'm using here for various of these various configuration for the tokenization mechanism. The first parameter is, of course, my text split, which is coming from my original data frame, and I'm just converting it to list format. And then the next one is split into words, which is a Boolean, and it denotes whether or not the input is already pre-tokenized, for example, split into words. And if set to true, the tokenizer assumes the input is already split into words, for instance, by splitting it on white spaces, which it will tokenize. Now, very important point here to remember that is split into words does not mean that the text was already pre-tokenized. This is not the case. It means that it just means that the string was split into words, not tokens. That is split on spaces maybe or other delimiters. And the next one is return overflowing tokens equal to true, which activates a chunking mechanism, also known as that it will generate more than one tokenized samples for text with more than 512 tokens. Next up, stride, which is I'm passing as doc stride. This is coming from our constant that we have defined in the constant file right here. So a doc stride, I have chosen 128 here. You can experiment with other values. So this parameter, this stride parameter that determines the number of tokens by which to slide the window or move the starting point of the next chunk while breaking the document into smaller pieces. For example, if you have a stride of 50 tokens and a maximum sequence length of 200 tokens for your particular chosen model, the first chunk will consist of tokens 1 to 200. The second chunk will be 51 to 250. The third chunk of tokens will be 101 to 300 and so on. So the stride parameter also determines how much will be the overlap between two chunks. And then return overflowing tokens equal to true. So beside creating the extra samples for long text, this particular parameter sets the key overflow to sample mapping in the resulting dictionary, which has the index of the original text that generated each of the samples. So this encoded variable will have my tokenized form of these text split, and if you actually pass a print statement here like encoded.keys, you will get these keys. That is, it will have input IDs, attention mask, and overflow to sample mapping. All right, and beyond these tokenizer calculation, this whole method that is tokenize returns these encoded or tokenized object, but after adding some extra information like these encoded labels right here and encoded widths. Now, as to the encoded labels, it is just we get that by applying these get labels for word IDs that we just discussed. And for encoded widths, this information can be useful later to map back to the original words in the input text, especially when dealing with chunked text. By replacing the non-values with -1, it ensures that the list only contains integer values, making it easier to work with downstream processes. Note that these encoded widths, this particular list is getting its value from word IDs, and the word IDs method is coming from here. Word IDs I. So this method is from the encoding object of Hugging Face, and it returns a list of indices where each index corresponds to the original word in the input text for each token. It is useful when you want to map the tokenized text back to the original words. And finally, you invoke or execute those tokenized method in the Jupyter notebook like this on both the dftrain and dfval. With all other arguments passed, and then you get your tokenized object from these as output of this method of tokenize. And this is your output. I'm just printing the tokenized train here, so you get your input IDs, attention mask, overflow to sample mapping, all these keys. All right, so after the tokenization, my dataset is fully ready, so I need to define a DataLoader class, and that's what I'm doing here. And it's very standard boilerplate code. That is, I have this DataLoader class and init method, get item, and len, all standard procedures here. And then you invoke or execute these class and get your dstrain and dSvalidation. And in both the cases, you pass your tokenized train and tokenized val. And then to get your actual data loader, you bring in this data loader module of PyTorch, and to this you pass your dstrain. Also mention batch size, shuffle equal to true, number of workers 0 here for because I'm running these in a Windows environment and there was some error I was getting, so I had to forcefully give it num workers as 0. But you can, if you are in the Linux environment or Unix environment, you can check out by giving different numbers to make use of all of your CPUs. And also pin memory true. And after the data loader, you just define the model. Here I'm defining config model, and then passing the model to the GPU device. And before starting the actual training, I need to define, of course, the train method. And here in train.py, that's where I am in my all-important train method. So let's quickly go over it. So first, this block here, the optimizer has multiple parameter groups, each with its own learning rate and other optimizer related settings. So the loop iterates over these parameter groups here. So this block just updates the learning rate of the current parameter group, and taking it from our config constant that we have defined in the cons.py. And then in this line, after updating the learning rates for all parameter groups, the learning rate of the first parameter group is stored in the variable LR. This is mainly done for logging purpose, as the updated learning rate is printed in the next statement right here. And then here I'm just defining a couple of variables which will be updated continuously in this loop right here. So training loss, training accuracy, and then these two important parameter or values or variables I'm defining, they are pretty much counter. So let's go through them. So these first variable num of train example counter, this variable keeps track of the total number of training examples processed so far in the current epoch. And each time the loop iterates over a new batch, the size of that batch will be added to the number of train examples counter. This variable helps to compute the average loss or accuracy over the entire epoch. And then the next one, which is num of train steps counter. This variable keeps track of the total number of training steps or training iterations completed so far in the current epoch. A training step is defined as one update to the model's parameters using a single batch of data. So in each iteration of the loop, num of train step counter is incremented by 1. This variable is used to compute the average loss or accuracy over the entire epoch and can also be used for logging purpose or to trigger specific actions at certain intervals. For example, learning rate adjustments or checkpoint saving, etc. So here in this line, I am starting a loop that iterates through all the batches produced by the data loader. In each iteration, it retrieves the index and the current batch of data. The index is useful for logging purpose, performing operations at specific intervals, or also for debugging. And the batch contains the input data and labels for the current set of examples. Alright, here in this particular line, I'm extracting the input IDs tensor from the current batch, which represent the tokenized input sequence. Then here I'm extracting the attention mask tensor from the current batch. The attention mask is used to indicate which element in the input sequence should be attended to and which should be ignored. For example, a padding token should be ignored. And then labels, these extracts the labels tensor from the current batch, which represents a true label and notation for each token in the input sequence. And then you apply the model and with the input IDs, attention mask, and labels, and you get your loss and raw target output logics. And after you get your loss, you just update the training loss because this is an accumulator variable. And then also update the other two accumulator variables, that is train steps counter. You increase it by a single number, 1, and also the number of train examples counter, and then you increase it by the first dimension of labels.size. And then you start, and that's your loss step because your loss step is just the accumulated training loss divided by number of train steps counter. All right, and now here I am starting to compute the training accuracy. So first I flattened the labels and with the labels.view a -1. So this line actually reshapes the labels tensor from a shape of batch size by sequence length to a flattened shape of batch size times sequence length. And this is done to simplify the computation of accuracy by treating all tokens in the batch as independent examples irrespective of their original sequence. And the -1 in the view function here is a placeholder that instructs PyTorch to automatically compute the correct size for that dimension based on the original tensor's shape. And the next line here, similarly, I'm pretty much flattening the active logics as well here. So this line reshapes the raw target output logits tensor from the shape of batch size by sequence length by number of labels to a flattened shape of batch size times sequence length and then number of labels. The logits reshapes the model's output for each token and label class. By reshaping the logit in this way, we can efficiently compute the predicted label for all tokens in the batch using the next line of code, that is this one. So here in the flattened prediction, this line computes predicted labels for each token in the batch by selecting the label class with the highest logit value, that is the most likely label according to the model. The torch.argmax function is applied along axis equal to 1, which corresponds to the num labels dimension in the active logits tensor. The output flattened prediction will have the same flattened shape, that is batch size times sequence length, as the flattened labels. And then in this line, that is active accuracy equal to labels.view -1 not equal to -100. This will generate a boolean. So this view -1 function is used to reshape the labels tensor into a one-dimensional flattened tensor, and the -1 in the view function is a placeholder that instructs PyTorch to automatically compute the correct size for that dimension based on the original tensor shape and size. And the full line creates a boolean tensor by performing an element-wise comparison between the flattened labels tensor and the value of -100. And then in the next two lines for the labels and predictions, I use torch.masked select. So for this line here, it returns a one-dimensional tensor containing only the elements of flattened labels where the corresponding element of active accuracy are true. Similarly, for the prediction, it uses again the active accuracy mask to filter out the predicted labels corresponding to the padded or irrelevant tokens. That is where it is not true. The result is a one-dimensional tensor containing only the predicted labels for the active tokens, that is non-padding and relevant tokens. And I just wanted to quickly discuss how this torch.mask tensor works. So the input tensor is flattened into a one-dimensional tensor with a shape of n, where n is a total number of elements in the tensor, and the mask tensor is broadcasted to the same shape as a flattened input tensor. The broadcasted tensor has a shape of n, and each element of the tensor corresponds to the corresponding element of the flattened input tensor. The function selects the elements from the flattened input tensor where the corresponding element in the mask tensor is true, and the selected elements are then returned finally as a one-dimensional tensor. All right, now that you have your one-dimensional tensor of labels and predictions, you can calculate your training accuracy. So first, I'm going to calculate this temporary training accuracy, which will be updated. So for that, I use this accuracy score method, which we have imported from sklearn. And then update in the next line, update the training accuracy by accumulating the temporary training accuracy. All right, and then this is another important steps to avoid any exploding or vanishing gradients, which is clip grad norm. So this method applies the gradient clipping to the gradients of the model's parameters and not to any other tensor or variables, because it is designed specifically for the purpose of preventing the gradients from becoming too large during training. So the model.parameters method right here returns an iterator over all the trainable parameters in the model. This includes the weights and biases of all the layers in the model, and then max norm equal to config max grad norm. This is coming from our constant that we have defined. This is the maximum allowed norm for the gradients. If the norm of the gradients exceed this value, the gradients will be rescaled back so that their norm is equal to the max norm grabbed from the config dictionary that we have defined right here in the const. Max grad norm equal to 10. And the norm of the gradients refers to the magnitude or length of the gradient vector, which is a vector that contains partial derivatives of the loss function with respect to each of the model's trainable parameters. The norm of the gradient is calculated using some norm function such as the L2 norm, which is defined as the square root of the sum of the squared elements of the gradient vector. And after clipping the gradients, I am applying 0 grad because I need to set the gradients of all the learnable parameters in the model to 0. This is typically done at the start of each iteration during the training process. The reason for setting the gradients to 0 before computing them is that PyTorch accumulates gradients by default. That is, the gradients are not overwritten but added to the existing gradients. Therefore, if we don't set the gradients to 0 before each iteration, the gradients will accumulate, resulting in incorrect update to the parameters. Then loss.backwards, which will compute the gradients of the loss function using automatic differentiation with respect to all the learnable parameters in the model. And finally, optimizer.step, which is used to update the model's parameters, that is weights and biases, based on the computed gradients. It applies the optimization algorithm defined by the optimizer, for example, ADAM or SGD, to adjust the model's parameters in a way that minimizes the loss. And then I am out of the loop, so I update my epoch loss and training accuracy, and also do torch.save to save the model's state dict. And also I empty the cache from the CUDA, that is GPU memory, and also gc.collect to do the garbage collection. And then just some printing logging stuff going on here. Nothing very super important here. All right, so that's my training function. And coming back to our Jupyter notebook, this is where I apply this train method. So when I'm running this training pipeline here, I go through each of the epoch, and that is where my train method is executed. So I pass model, optimizer, and data loader train and epoch. And the next step, immediately after training, I also do the validation pipeline. And this we will discuss in a second, but this is where this validate method is actually defined in our validation.py, right here. So so that pretty much the final step for this notebook, because this is just a training notebook. Inference is done separately. So this very much is a last step in this notebook, but let's go through the validation workflow. So in the validation.py file, I have 3 methods actually. I have an inference method, I have a get prediction method, and both of them I use within my validate method. And this validate method is the one that we see right here. So let's go through them. So this inference method will just take a data loader and the model, and it will return the final predictions. And in terms of the working of it, so I just define 2 default dict here, predictions and scene word index, and then I loop over each batch from the data loader and get their input IDs and attention mask, pass them to my GPU device, and the output of the model is I just execute the model method here, execute the model and pass IDs, attention mask, and return dict equal to false. And then I get the batch predictions by applying torch.argmax, and from the outputs I take the 0th element. So here output 0, this particular thing here is a tensor which contains a logits, that is a raw output values for each token representing the probability distribution over all possible label classes. And then torch.argmax function is used to find the index of the highest value, that is the most probable class, along the last dimension, which is x is equal to -1 of the logits tensor. And this index corresponds to the predicted label for each token. It is needed because the model's output is in the form of logits, which are not directly interpretable. By using torch.argmax, we can obtain the predicted label indices that are easily understandable and can be mapped back to their corresponding string labels for evaluation or further processing. And then I start this loop right here. So what I do here is go over each prediction, getting the text ID reference. Now here, batch spreads contains a predicted label indices for each token in the batch. And this particular thing, that is batch and then overflow to sample mapping to list. This list maps the predicted labels back to their original text IDs. It is necessary because the input text may have been split into multiple chunks due to the token limits or other reasons, and we need to keep track of which part of the original text each prediction belongs to. And then I apply the zip function. So the zip function just combines both batch spreads and the second element and create a element-wise pairs of each of them, which is what I get with these chunk spreads and text IDs. And then these word IDs, are absolute references in the original text, and the chunk spreads here I map from IDs to labels. And IDs to labels, remember this line is needed because the model's output is in the form of label indices, which are not directly interpretable. By mapping these indices to their corresponding string labels, we can easily understand the predicted named entity types for each token and evaluate the model's performance or use the predictions for future processing. And just for reference, this is that IDs to label variable. So we have so many labels which are named entity types or discourse types in this case, and the IDs are actual numerical indices for each of them. And then I start this loop right here, enumerate word IDs. And this block that you see here, if the word index is -1, the loop should do nothing and continues to the next word index. This is because -1 represent a padding token or a special token that doesn't have a corresponding word in the original text. And so I pass. And then otherwise, that is L under the elif condition. So here I need these variables, seen word index, which was declared right here initialized with a default dict. And so this will ensure that each word in the original text is assigned a predicted label only once, even when it appears in multiple overlapping chunks. And that's exactly why when I do this, that is word index not in seen words text ID. This checks if the current word index has not been processed for the given text ID. This is done to avoid processing the same word multiple times when it appears in the overlapping chunks. Because remember, we have a stride parameter here. So some chunks, each of the chunk will have some common portion. And yeah, so after that, predictions text id.append, I add the chunk preds idx. So add the prediction if the word does not have a prediction from a previous chunk. Also, in the next line, add the current word index to the seen word index dictionary so that we can check it again in the next loop. All right, after these two loops are over, I finally return from this method these final predictions, which is the final outcome from this method. And this inference method I'm going to use later, but let's first go over this get predictions method as well. So these, one second, this get prediction method actually, all right, after these two loops are over, this final prediction is a variable that I return from the entire method. And the last line is just a list comprehension that iterates through each sorted keys and retrieves the corresponding value, that is the predicted labels, from the prediction dictionary. And it sorts the keys in ascending order, ensuring that the final predictions are in the same order as the original text. And after that, I define these get prediction. That's another method that will be used in our validation pipeline here. So these get prediction, this function generates entity prediction for a given data frame using a specified model and data loader, and it returns these df pred variable, which is a data frame containing entity prediction for each input in the original data frame. So let's see how it works. So first I just apply or invoke the inference method that we defined earlier and get the predicted labels. And then I have to start two loops here. So one is this for loop and another one is while loop. So in the for loops, I just go through the entire length of the data frame. And remember here, this data frame is the data frame which contains the input data for which predictions will be generated. And so when I do idx df.id.values, it will get the extract the ID of the current input from the data frame. And then in the next line with the spread predicted labels I, this one will get the predicted label corresponding to the current input. And then I start this while loop with j equal to 0 and go through the entire length of the spread variable and first assign the label at index j from the predicted labels spread to the variable CLS. And CLS equal to O pass. That means that if the current label is not O, if the current label, that is the current CLS, is O, representing no entity, then the code will skip to the next step. And if the current label is not O, this line replaces B with I. I'm talking about here. And this is done to consider B and I tags as the same, simplifying the task of extracting the entity. The reason for replacing B with I in this line is to treat both B and I tags as the same for the purpose of extracting entities. By doing this, we can easily identify and extract the entire entity by looking for a continuous sequence of the same I tag. This simplification makes it easier to find the start and end indices of the entities in the input text. And then declare another variable end, which is j plus 1. So this line is done because we want to start looking for the end of the entity from the next position in the predicted labels. And then I start this while loop, while end is length of pred. So it starts a while loop that iterates through the predicted labels starting from index end, and the loop continues as long as the following conditions are met. So this is the condition right here. And the conditions are that the end, this variable, is less than the length of the pred, which will ensure that we don't exceed the boundaries of the list. And also the label at index end, that is spread end, is equal to the current label class, indicating that the current entity is still continuing. And then I just increment end with a plus equal to 1. So this line increments the value of end by 1 in each iteration of the while loop, and overall this ensures that the loop progresses through the predicted labels until it finds the end of the continuous entity or reaches the end of the list. The significance of this block is to identify the continuous sequence of the same entity label in the predicted labels, which represent a single entity in the input text. By finding the start and end indices of this continuous sequence, we can effectively extract the complete entity from the input text. And then I apply another condition here, that is CLS is not equal to O, CLS not equal to empty, and and end minus j is greater than 7. So these respectively means is that the current label CLS is not an outside entity representing O. It is not an empty string, and the length of the continuous entity sequence is greater than 7. And only then, if the above conditions are met, then append a tuple to the final preds list with the following elements. And what are the elements? The first one is IDX, what you see here, which is the input ID from the original data frame. Then I do CLS.replace I dash with an empty string. The predicted entity class with the I dash prefix is removed. Note that earlier we have already replaced all the beginning token, all the beginning tag, with I. So here I will be left with I dash only. And then finally join with a map and str and list. So this entire expression And this entire expression of join and then apply map and then do a str to convert it to a string and then apply list range. This entire expression, it represents a string of space separated indices corresponding to the predicted entity in the input, created by converting the list of indices from j to end to a string representation. And also this end minus j greater than 7, this condition is a filter to only include entities that span more than 7 tokens in the input text. Depending on the problem at hand, this threshold may be adjusted or may be removed altogether to include entities of any length. So that's the significance of that. So this entire block here, this one I'm talking about, the significance of this block is to extract the entity information from the predicted labels, filter entities based on the length threshold, which is 7, and store the final entity prediction in a structured format. And that's it. After that, you just update the j to be the end so that I can go forward with the next loop. And then when the entire while loop is done, I'm out of these two loops, and that will be my final data frame that is going to be returned from this method. The only thing I do here is to add 3 columns. All right, that ends my get predictions, and the only method I'm left with is validate, which will implement this get prediction method. And the validate method is rather easy. First, you just put the model in the eval mode, and then you get your df valid, which is your list for the valid dataset. And then you just implement the get prediction method, pass it your validation data frame, your validation data loader, and a model. And with that, you will get your out of fold data frame, which will have 3 columns like we saw, ID, class, and prediction string. So then I'm just extracting all the unique classes with this line right here. And then I am going over each of the classes from these classes array. So here, when I'm doing this looping for C in classes, first I'm creating a new data frame preddf by filtering the out of fold data frame for rows where the class column matches the current class C. The copy method is used to create a copy of the filtered data, ensuring that the change made to preddf will not affect the original out of fold data frame. Out of fold contains the model's predictions for the validation dataset. By creating preddf, the function can focus on the performance of the model for the specific class C when calculating the F1 score. And the F1 score I get by applying this compute macro F1 score. This method is actually coming from another method that I have defined in the utils. Yeah, here, compute macro F1 score. But this 2 method actually is for calculating the F1 score, which I have discussed in detail in my other video, the link of which I will give here. You should check it out because I have gone through each of the steps of these 2 methods here. And very much these 2 methods are just implementing this particular Kaggle competition's evaluation pages instruction. So there they have given 3 rules how the overlap should be calculated between ground truth and predictions, and how the F1 score should be calculated. So this 2 method is just implementing those rules. And anyway, I have given, you will have access to this code, and there will be detailed comments in that code. And also you can go through my other video to go through each step of these 2 methods. All right, coming back to validate. And then only a few more simple steps. You get the F1 score for this class. You append this F1 score to a list F1s. And finally, at the end of the function, you just calculate the mean, np.mean of those collection of F1 scores. And that's what very much this function do, validate. All right, now coming back to the Jupyter Notebook, the final step is actually just doing, executing this validate method, which will give you the mean F1 score on your validation data set. All right, so this was the training on these competition. Remember again, this is not the inference, only the training part of the code. So probably I will do the inference in a separate video. So here the training ends, and after going through 5 epochs, I get this final trained model, which is saved in our path with this name PyTorch model.bin. Alright, that's a wrap, and do stay tuned because I'll be doing many more NLP projects and also many Kaggle competitions over the coming weeks and months. So see you in the next one. Thank you very much for watching.